Hi, so we will now take a look at a technique where even after adding slack and surplus variables to our equations, we are unable to solve or identify the basic variables. And that technique is called as two-phase simplex method. We are given an objective function to maximize z is equal to 6x plus 3y, and constraints are x plus y is greater than equal to 1, 2x minus y is greater than equal to 1, 3y is less than equal to 2, and or non-negativity constraints x is greater than equal to 0 and y is greater than equal to 0. If we apply the technique that we learned with the simple simplex method, we will convert this to our standard form. The objective function is maximized, so it is fine. Maximize z is equal to 6x plus 3y. Let's try to convert the constraints to our standard form. In this case, it is greater than equal to 1, so we have to subtract a surplus variable. Pay attention to something that we've added here, which is called a1. I'll talk about it in a few minutes. For constraint number 2, we have to subtract a surplus variable s2. And constraint number 3, we have to add a slack variable s3. We have basically subtracted two surplus variables and added one slack variable. Now let's pay attention to what we have added as a1 and a2. a1 and a2 are called artificial variables, and in this case we have two of them. And the reason to add these two artificial variables is since if we do not add these variables and you look at the equations, you cannot get a canonical form otherwise. That means your tabular 0 cannot be obtained. There are no basic variables to start with. In such cases where we are unable to identify any basic variables, we have to add an artificial variable. And by adding these artificial variables, we have to add a series of steps to get to our first tabular. So let's take a look at the new method. Because we have added artificial variables, we have to temporarily change our objective function, and that is the phase 1 of this method. If we say that a1 plus a2 have a minimum value of 0, and given that individually a1 and a2 are both greater than equal to 0, then we can say that both a1 and a2 are individually equal to 0. Might sound confusing, but the bottom line is if a sum of two positive numbers is equal to 0, that means individually those two positive numbers are equal to 0. And that's how we will derive our objective function of phase 1. So for phase 1, we try to minimize a1 plus a2, that is the sum of the artificial variables. Since we have only two, we will minimize a1 plus a2. And since our standard form is maximize, minimize a1 plus a2 actually is equal to maximize the negative of a1 plus a2. So our objective function temporarily becomes maximize w, which is given by a negative of a1 plus a2. Now we will transform that into our tabular, and here is the tabular. So we see that our first constraint has coefficient of x as 1, coefficient of y as 1, s1 is negative 1, a1 is 1, and right hand side is 1. And similarly, we have the second row and the third row. Now, since a1 and a2 are part of constraints 1 and 2, let's see what is the sum of a1 plus a2. So what we'll do is we'll simply take sum of constraints 1 and 2, and we get x plus y minus s1 plus a1 is equal to 1, and if we sum 2x minus y minus s2 plus a2 is equal to 1, the right hand side sum becomes 2, and the left hand side becomes x plus y minus s1 plus a1 plus 2x minus y minus s2 plus a2. So now if we rearrange this and take a1 and a2 on the right hand side, the equation turns to 3x minus s1 minus s2 minus 2 is equal to minus a1 plus a2. And in this case, if we now replace a1 plus a2 with the negative sign as w, we get w is equal to 3x minus s1 minus s2 minus 2. So our temporary objective function for the tabular is based on this equation w is equal to 3x minus s1 minus s2 minus 2. And if we take the variables on the left side, we have the coefficient of w as 1, coefficient of x as minus 3, the coefficient of y is 0, s1 is 1, s2 is 1, and then the right hand side is negative 2. You do want to notice that we still maintain the original 0 as a R4, and again we will take the right hand side variables onto the left, so z is equal to 1 in this case, x is equal to minus 6, y is equal to minus 3, and rest of all are 0. Now we will actually continue with the same process of identifying the basic variables, and our basic variables for Tableau 1 are given here: A1, A2, S3, Z, and W. So in this case, A1 is basic, A2 is basic, S3 is basic, Z is basic, and W is basic. So this is now a canonical form. So we look at this, X has a negative variable, and that will be our pivot column. And in this case, we are looking at the W row, the last row. And the ratio of right hand side becomes 1 divided by 1 is 1, 1 divided by 2 is 1 by 2, minus 2 divided by minus 3 is 2 by 3. We identify the leaving variable will be A2 and the entering variable will be X. So let's do that. So now instead of A2, we have X as the basic variable, which means we have to perform some EROs because this is not basic. The EROs are R1 is assigned the value of R1 minus R2 by 2, R2 is assigned R2 divided by 2, R3 is assigned R3, R4 is assigned R4 plus 3 R2, and R5 is assigned R5 plus 3 times R2 by 2. Again, just reiterating that how do we know which rows are part of an operation? The idea is simple, that you have to pick up the row that you're working on and the pivot row. So the operation of first row has to be between R1 and R2, and the intent is that I have to make everything in the column X 0 because I'm transforming X row 2 here as a basic variable, except row 2, all these values in each row should be 0. So in row 2 I can work with R2, in row 3 I can work with R3 and R2, in row 4 I can work with R4 and R2, in row 5 I can work with R5 and R2. And once we do these operations, now the Tableau is in canonical form and we have to identify the next entering and exiting variable. So we know that there is still a negative value in the last row. In this case, our objective function temporarily is W. So we identify this as our pivot column. The right hand side values ratio is given by the division of right hand side value divided by 3 by 2. So 1 by 2 divided by 3 by 2 is 1 by 3. 1 by 2 divided by minus 1 by 2 is minus 1. 2 divided by 3 is 2 by 3. 3 divided by minus 6 is minus 1 by 2. And minus 1 by 2 divided by minus 3 by 2 is 1 by 3. Clearly the smallest positive number here is 1 by 3. So our exiting row or pivot row becomes row 1. And we have to, the leaving variable is A1 and the entering variable is Y. So what we do is Tableau 2 of phase 1, we have to perform the following operations, and this is what I get after performing those operations, that R1 is changed to R1 by 1.5, R2 is changed to R2 plus R1 by 3, R3 is changed to R3 minus 2 multiplied by R1, and then R4 is changed by R4 plus 4 times R1, R5 is changed to R5 plus R1. And now we see that as a result of this, we do not have any more negative. That means phase 1 is now optimal. Also, we should note that artificial variables A1 and A2 are not basic. That means they are equal to 0. and hence our assumption that W minimizing A1 plus A2 has a value of 0, which means individually A1 and A2 are equal to 0. Now we will start with our phase 2, and phase 2, what we do is we drop the artificial columns and then we drop the W row. So our table now has tabulo 0 here of phase 2, and we have our basic variables identified: y, x, s3 and z. And let's see, y is basic, x is basic, z is basic and s3 is basic. Let's identify the pivot column, and in this case it will be -4, and then we have to identify the leaving row, and the RHS divided by coefficient values are shown here. So the leaving row is 1/2. Our table is shown here, and we have the operations as R1 is assigned R1 plus R3/3, R2 is assigned R2 plus R3/6, R3 is assigned R3/2, R4 is assigned R4 plus 2 times R3. So we have tabular 1 phase 2 now, and we have to identify what is the next pivot column. The next pivot column is -3. However, we have an issue in this case though, that we cannot find anything that is positive on the right hand side divided by coefficient. So what it means is that this particular problem has a unbound solution, and when this happens we are reaching an unbound LP where the objective value is reaching either a positive or a negative infinity. So just to recap, what we did in the two-phase algorithm was that since we had to add artificial variables in addition to surplus and the slack variable, we had to split the solution into two phases. Phase 1, where we minimize the sum of artificial variables or maximize the negative of sum of artificial variables, and once we are able to solve the phase 1 where we find that the phase 1 is now in an optimal solution form, all the artificial variables were equal to 0. Then what we did is we took the output of phase 1 and removed all the columns of artificial variables, and also we deleted the temporary objective function. Then we started with that state of the tabulo as tabulo 0 of phase 2, and the process then continues to find the solution using the regular simplex algorithm. However, in this particular case we could not find a solution because even though the tabulo in this phase has a pivot column, we are unable to identify a pivot row because we do not have any positive number in the ratio of the right hand side to coefficient, and this particular case is called as an unbound LP. Let's look at the graphical representation of unbounded LP. So what I did is I basically plotted the constraints onto a graph, and you can see that the area that is feasible is given by this orange part and which extends to infinity. Now, as a exercise, what if this was a minimization problem? So this is one of your homeworks. If the same problem that we solve for maximizing is now minimized, I would like you to solve this using the two-phase simplex method. Final terminology and definitions. What are restricted and unrestricted variables? Basically, variables that are limited to be positive or negative only are called restricted. That means they vary on only one side of the number line. The unrestricted variable can take any value on the both sides of 0 on a number line. An optimal solution is a feasible solution that satisfies the objective function. That means it either maximizes or minimizes it. We just saw an unbounded LP. and unbounded LP is where we can drive the objective value to positive or negative infinity. An infeasible LP is when the feasible region is empty. That means there is no feasible solution. And an alternate solution is when there are alternate or multiple optimal solutions. We saw that in the previous lectures. And here's a new term that we are introducing. It is called degeneracy, which means that one may end up in performing extra iterations if one of the basic variables takes a value of 0. This is the limitation of a simplex method, that if one of the basic variables takes a value of 0, then you may have to perform some extra iterations, because replacing that basic variable will not going to change the objective value. And the indicators that we see while we are using the simplex method are: an optimal solution is reached if there are no negative values in the objective function row. We've used that. Then an optimal non-unique function is attained when any non-basic variable in the optimal solution has a value of 0 in the objective row. And unbounded, we just saw that when no ratio of the right hand side value in the row and the coefficient of entering basic variable is greater than 0, then we have an unbounded solution. And an infeasible solution is if the right hand side value of the constraint variables ever becomes negative, or in two-phase method the artificial variable still stays basic after phase 1 is optimal. And then degeneracy is one or more basic variables takes a value of 0.